This section of the lesson will tell you how the stall speeds quoted in aircraft flight manuals are determined and the parameters on which they are based. Aircraft need to fly at low speeds with high angles of attack during takeoff and landing in order to keep the required runway length to a reasonable minimum. But there must be an adequate safety margin allowed between the minimum speed for normal operations and the stalling speed. During the flight testing that takes place before type certification, prototype aircraft are stalled, and the stalling speeds established for inclusion in the flight manual. The stalling speed for small aircraft, those in the EASA category CS23 for normal, utility, aerobatic and commuter aircraft, is based on the stall speed in the landing configuration VS0 and the speed for a given configuration VS1. For large aircraft in EASA category CS25, a reference stall speed known as VSR is used. VSR is a calibrated airspeed defined by the manufacturer and may not be less than a 1G stall speed. It is expressed in formula form as being equal or greater than VCL max over the square root of NZW, where VCL max is the calibrated airspeed obtained when the load factor-corrected lift coefficient first reaches its maximum during the lay-down test manoeuvre. In addition, if the aircraft is fitted with a stick pusher, a stall prevention device described in the next section of the lesson, VCL max may not be less than the speed at which the device operates. NZW is the load factor normal to the flight path when the aircraft is at VCL max. For an aircraft without a stick pusher, the speed at which it reaches its CL max at 1G, in other words its 1G stalling speed, can be considered to be its VSR. For the purpose of the test, to determine VCL max, the aircraft is flown with the following conditions: 0 thrust at the stall speed, propeller pitch, RPM controls, if applicable, at the takeoff setting, landing gear and flaps set as appropriate to the performance standard being tested, the weight to be that applicable when VSR is being used as a factor to determine compliance with the required performance standard, the centre of gravity to be in the position that results in the highest value of VSR, and the aeroplane must be trimmed for straight flight at a speed determined by the manufacturer, between 1.13 VSR and 1.3 VSR. During the test, the aeroplane must be decelerated from the trim speed at no more than 1 knot per second. An additional condition, which applies when the aircraft is fitted with a stick pusher, is that the reference stall speed may not be less than 2 knots or 2%, whichever is the greater, above the speed at which the device operates. VSR will vary with each of the conditions specified. Factors which affect VSR are thrust in excess of 0, wing contamination and load factor. One thing that does not affect indicated stall speeds, however, is density altitude. The EASA regulations and their equivalents outside Europe specify that there must be clear and distinctive warning of a stall, sufficiently in advance of the stall for it to be avoided, both in straight and turning flight, and with the landing gear and flaps in any normal position. The warning can be provided either through the inherent aerodynamic characteristics of the aircraft itself, such as buffet, or by means of a device that will give clearly distinguishable indications under expected flight conditions. However, a visual warning that requires the attention of the flight deck crew will not suffice on its own. There must be a tactile or audible warning as well. A warning device must provide a warning in each normal configuration. Regarding the speed at which a device operates to give adequate stall warning, known as VSW, it should begin no less than 5 knots, or 5% of CAS if greater, above the speed at which stall recognition would occur, and should continue to operate until the angle of attack is reduced to about the angle at which it began. Under the same conditions, but also in straight flight, at idling power, and with the C of G which gives the maximum VSR, there should be a minimum of 3 knots or 3% of CAS above VSR. The regulations also stipulate that the warning margin must be sufficient to allow the pilot to prevent a stall if recovery is initiated 1 second or more after the warning in a 1.5 G turn, decelerating at 2 knots per second, with gear and flaps in any normal position, and with power and trim set for straight flight at 1.3 VSR. Finally, stall warning must also be provided in each abnormal flap or slack configuration likely to be used in flight following system failures, including all configurations covered by flight manual procedures. It is possible that adequate stall warning will be provided by the airflow separating fairly early and causing buffet over the wing and tail plane, but this is often insufficient, and so a device which simulates or substitutes for aerodynamic buffet is usually fitted. Artificial stall warning on small aircraft is usually given by a buzzer or horn, but on modern large aircraft a stick shaker is used in conjunction with lights and a noisemaker. The stick shaker is intended to represent the aircraft's natural buffet by replacing it with a tactile warning. The noisemaker is added in parallel to ensure that the warning is noticed if the pilot's hands are not on the controls. For example, if the autopilot is engaged. The device consists of a pair of electric motors, one on each control column, and rotating an eccentric weight to generate vibration. Artificial stall warning devices can receive their signals from a variety of detectors, all of which are activated by changes in angle of attack. The leading edge stall warning vane, or flapper switch, usually used on small and medium-sized aircraft, is positioned so that at normal angles of attack, the airflow holds it down. But as angle of attack increases, the stagnation point moves down and back around the leading edge, and the change in pressure raises the switch, making the contact. The alpha vane is mounted on the side of the fuselage and trails in the relative airflow. The fuselage effectively rotates around it, and the vane thus senses the angle of attack. The stick shaker is activated at the appropriate alpha value. Another fuselage-mounted device is the angle of attack probe, consisting of a lateral tube with slots or holes sensitive to changes in the relative airflow, which generates the necessary signals as alpha increases. All of these devices sense angle of attack, and therefore automatically take care of changes in aircraft mass. The alpha vane and probe can also compute the rate of change of alpha and give earlier warning in the case of faster rates of approach to the stall. The detectors are usually datum compensated for configuration changes, and are always heated or equipped with an anti-icing facility. There are normally sensors on both sides of the fuselage to allow for any asymmetric airflow due to side slip.